Lesson 23. We're talking about ellipses here. Now, what is an ellipse? We know based on conics that if we cut it in an angle, if we cut the cone in a specific angle, I'm going to draw that right here. So if I take myself a cone here, okay, and I cut it in some way with a plane like this, you're going to see this object that is angled in some way. So it's not a perfect circle anymore. It's actually this slight bent circle. Okay. Now, how would we define an ellipse? Well, in terms of geometrically, not just visually, you have an ellipse as a set of all points in a plane, the sum of which whose distances from two fixed points, which those fixed points we're going to refer to as foci, is a positive constant. Now, I'm going to revisit this definition a little bit later, so I'm not going to draw these lines. If you want to draw these lines here, you can actually see that in your textbook. Now, let's go through definitions. The longer axis of an ellipse is called the major axis. Foci are located on this axis, as well as the vertices are. The center of the ellipse is the midpoint of the axis. Lastly, the endpoints of this axis are the vertices. Again, that's right there. The shorter axis is the minor axis. Now, for number 5, we're going to go ahead and draw this picture. So number 5, it says, draw an image below that identifies the major, min, the foci, and the vertices of an ellipse. I'm going to draw my set of axes here. Okay, there's my x and my y axes. And I'm going to go ahead and plot points that are supposed to be appropriate to an ellipse. And I'm trying to do this to the best of my ability so it doesn't screw up here. And that there is probably the best ellipse that you're going to get from me. Now, when we're trying to label all the details, okay, the vertices are specifically these endpoints right here. This one and this one are the vertices. These two are not. Now, that's weird, I know, but they're not considered vertices. The vertices are specifically the endpoints of the major axes. Okay, so that line there is the major axis. The minor axis just tells us where the other endpoints are going to be. That's what that is right there. That right there is the minor axis. Now, the major and the minor axes intersect at a point. That point is considered the center. And more importantly, the center actually bisects the major axis and the minor axis. Okay, that's going to be very important for later use. Lastly, somewhere on this line, inside, those 2 points there, those points that are the x's, those are my foci. Okay, so keep in mind that, notice, from the vertices, just like we did in the parabola, we are circulating around the 2 foci. Okay, we're bending in towards the foci in the ellipse. So that covers number 5. Let's talk about question number 6. And I told you we'd revisit that whole definition. So it says, what is the positive constant that is equivalent to sum of distances between the foci and a point on the ellipse? And now you're thinking, what? There's a lot of stuff going on there. So let's reread that with the idea of an ellipse in mind. Well, let me go ahead and draw myself an ellipse here. I'm going to do this to the best of my ability so that it's nice and clean. Now, yeah, it's more like a circle, but that's okay. It's really not important how much of an ellipse it looks like. What's important is that I plot the foci appropriately. Okay, it says, what is the positive constant that is equivalent to the sum of the distances between the foci and a point? I'm going to call this foci, and I'm going to call this foci a specific thing. Let's call this one negative c comma 0. I mean, it is on the x-axis, so I'm going a negative direction of the x value, so I'm going to call it c. I actually go in the positive c direction, okay, on the other side. So these 2 points are equidistant from the center. Keep that in mind. Those 2 points are equidistant from the center. Now I'm going to read that question again. What is the positive constant? So I want k equals to something. Okay, I want a constant equal to something that is equivalent to the sum of the distances between the foci and a point on the ellipse. So the distance between this and this added together should be equal to that. Well, let's call that point x comma y. Well, if this is the case, I could actually find myself an equation here. The distance between xy and negative c comma 0 is just a distance formula. Remember? The square root of, we would go change in x's squared plus the change in y's squared. So the change in x's would be actually a x minus a negative c, and y minus 0. We also have the distance from this one to this one. What's that distance going to be? Well, that's going to be the distance square root of, now this time I'm going to have x minus c squared plus y minus 0 squared. And remember, I'm going to read the question again. What is the positive constant? What is k that is equivalent to the sum of the distances between the foci and a point? Those two pieces added together. Okay? So what is this k value? That's the real question here. Okay, what is it supposed to be equal to? Well, there's a very easy way to solve this particular equation. Now, before I actually try and do that, I'm going to do this. This is a square root of x plus c squared plus y squared plus the square root of x minus c squared plus y squared. Being very lazy, I should probably simplify this first so that it looks even a little bit cleaner. Okay, well, there might be a better way to identify this. Again, this is not pretty to solve, but in the last setup, we said that this is every set of points on this ellipse satisfies this property. Well, I'm going to label a few points here. Well, let me go ahead and label this vertex over here as, I don't know, a comma 0. Again, I'm just going to say that this point here is a distance of a from x, the origin, and then 0 up and down. So then this point over here, because an ellipse has a lot of symmetry in it, should be a negative a comma 0. What if I tried to pick that point? Again, what if I tried to pick, I could do the same thing with this point up here and just call this, let's just say 0 comma b, going up a distance of b, down here going down a distance of b. I could pick those points instead, as long as they satisfied the rule. Well, let's set this up very, very carefully. The distance from this foci to A, the distance from here to here, is going to be what? Well, I don't have to use a formula for that. I can see the distance. The distance is of value because it's not changing in y. The y's, notice, on this line are not changing. So what is the distance from this point to this point? And let me get out a red pen to do that a little bit more clearly. From this foci to this vertex, that distance will be c, distance of c plus the a. So that distance there would technically be a plus c. The distance from this one to this one is a plus c. Why? Because I have a distance of a and then a positive distance of c. Okay. Well, what would then my distance from here to here be? Well, if I have to go all the way out to a from the origin, I have to subtract that value of c, right? Again, if this whole distance is a, from here to here, I have to subtract c from it to make it appropriate. So the distance is actually, for that piece, a minus c. And if I add these two together, what do I get? Well, the c's cancel out, and I'm left with just 2a. Huh. That's interesting. The distance between any 2 points, because it always has to be constant. Again, it always has to be constant. The distance from one foci to a point on the ellipse back to the other foci added together will always be the value of 2a. Well, what's that value? What is 2a? Well, the distance from here to here is a. The distance from here to here is a. Well, wouldn't it be logical then that this thing being equal to 2a, this is actually the length of the major axes. Okay? Now, there's a lot of stuff going on here. Keep that in mind, that there's a lot of things that are being manipulated in all of this. What is most important is that if I were to set this thing here equal to the major axes, and manipulate this. Okay, you get it so that it's no more square root things. Okay, I will find out that my equation. Now, if you want to know how to do this, I'm not going to show it to you here. That's a lot of work and it's very unnecessary. Look in your book on page 714. It shows out all of the steps, all of the methods being done. I have faith that every single one of you can follow those steps and understand exactly what's happening. On the more complicated steps, they do actually show what steps they're doing, what they're doing to each side. What they end up finding out is after manipulating this equation right here equal to 2a, we get x squared over a squared plus y squared over b squared is equal to 1. Where a is the location of the vertex, and b is the location of the endpoints on the minor axes. Again, those are not vertices. Those are not vertices. So this right here, with the idea that this graph is what I'm playing with, gives us the setup for an ellipse centered at the origin. Okay, an ellipse centered at the origin. What we're going to do is actually skip 7 entirely. If you want to fill this in, there is a section in your textbook that you can follow. In my opinion, why waste our time using stuff at the origin, like we did with the parabola, if we can just go ahead and do the exact same thing at any generic point, okay, with a center at h comma k. So what we're going to do is in the next video, we're going to talk about this, and then we're going to go back through everything else.